This video is meant to explain the design process behind my 6th sanding robot prototype, which I made in a design team this fall. Originally, we were going to take an old wooden prototype and attach a counterweight system which would allow the sander to reach the edge of the beam, as the current prototype could not do this. But I was pretty sure early on that I wanted to go with this arm design, which would involve an arm that could lift and rotate a sander around a base that would drive the robot up and down the beam. The first step into realizing this prototype was to make a wooden prototype. I created an arm linkage and a rotating gear out of wood, and I assembled this into a prototype that we could test. It became clear in testing my original wooden arm prototype that the NEMA 17 stepper motors I was using did not have enough torque to lift the arm with the sander attached. So I bought a 5-to-1 gear reduction stepper motor online, and I began playing with that. Next step in building a sanding robot was to turn some of the wooden parts into plastic parts. Once the arm and the rotating intermediate were assembled, I could begin work on the base. My original design for the base was kind of thrown together out of wood, without much thought for how the chain-driven motors would drive the wheels that would actuate the sanding robot up and down the beam. In the process of buying our first parts, we also redesigned the arm linkages out of aluminum. Our manufacturing lead made them by machining holes just big enough for bearings to fit into. This is how I control two stepper motors using the Click C2-03 CPU and the C2-08D1. The C2-08D1 has two pulse train outputs, and right now I have a program wired up so that these two are the stop and start buttons, and these two are limit switches for this motor right here. This motor only turns on and off with the stop and start buttons. So when we go to start the motors, they both start. We can stop them both. We can also stop this motor using a limit switch. This would be the positive limit switch. So it stops just that motor. And it won't go again until we stop the program completely, start it again.
Yeah.
It wants to go, there's just like too much friction, and also the sander's not on. The problem with the wooden base is that the chain had to go through many transitions in order to wrap around the outer drive wheels and also wrap around the motor without slipping. Without proper idlers, I tried to use screws and bolts that rolled roughly across the screws in order to tension the chains.
Or just like determined testing or something.
Our first assembled prototype did not have enough power to drive the robot up and down the beam. With this disappointment from the first prototype test, I vowed to completely redesign the base and make it so that there was very little friction between the chain and the wheels that would drive the robot up and down the beam. Another thing I did was to make the wheels smaller. The original ones were 3 inches, I made the new ones 2 inches to provide more torque. Next came the part where I turned the plastic parts into metal parts. Today we're at the machine shop and we're bending our water jet parts. I already bent this one in the brake. The vertical that held the arm to the slew gear we decided to make out of sheet metal. This was again to reduce the amount of time taken to 3D print and also improve the rigidity. I designed the sheet metal water jet parts and then had them welded together at the machine shop.
you.
Okay.
Is that run already?
Yeah. Yeah, record. I spent several nights designing the CAD for the full base assembly. It was a mixture of 3D printed and water jet sheet metal parts. By the time I had all the 3D parts printed, it was about Thanksgiving time, and our design showcase was immediately when we came back from Thanksgiving break. So I brought all the parts home and assembled them in the workshop. To my delight, all the 3D parts fit together almost exactly as intended, with only a few modifications needed. So I realized these bolts right here would hit the motor, so I have to move them over a little bit. And to find the coordinate of where that hole should be, I worked out the radius of the circle and how far over I wanted it to go, which is 1/11/16. So that's where that coordinate comes from to maintain a circle. I'm gonna have to do the same on the bearing to drill a hole with it. Oh, it's just barely not long enough.
Here's another one.
One major hurdle I had to overcome with the old base was that the motors had nowhere to go, i.e. no room because the intermediate that rotated was in the way when the wings were pushed close together. The way I got around this was positioning the motors just right so that they could go inside of the base. A conversation I had with my teammate over dinner one night led me to cut out part of the gear and make it sheet metal so that the capacitive distance sensor would have something to sense as the gear rotated over it. One major thing I did to upgrade the rigidity of the machine was to upgrade the rotating bearing that the large slew gear sat on. The original bearings I used were made for Lazy Susans. The sheet metal was flimsy and it was hard to mount them with 3D printed parts and hard to design around them. I went and bought aluminum machined Lazy Susan bearing, which was much more rigid and also looked a lot better. The only modification I had to make to the bearing was to drill some new holes. My team also designed in CAD a new sander clamp to hold the sander more securely. flat part, this flat part lines up with the corner of the bolt, so that it goes like that. The only thing that runs up through the center of the slew bearing is the mains power and the 2 drive motor cables. All the rest of the wiring is kept above the rotation of the gear, so it's not a concern about most of the wiring getting twisted. Alright, well it didn't hit the thing, so... For control of this machine, all we needed were 2 buttons and 2 2-position toggle switches. These toggle switches allowed for adjustment of the beam sanding speed and also the width of the beam. One button was used to toggle between the modes of the toggle switches, and the second button was used as an e-stop to stop all processes of the program and reset the whole machine. I spent Thanksgiving break coming up with a simple program to run the machine for demonstration purposes at the design showcase. A previous video I made showed that I have since upgraded the program to fully sand a beam as I've intended. Once the sanding robot was fully assembled and Thanksgiving break ended, I brought it back to the school. With it being the dead of winter, I haven't had much opportunity to fully test the machine, but I'm fairly confident it will work. All the white plastic you see on the robot is white ABS plastic. All the black plastic you see is PLA, and the metal you see is 1/8 inch steel plate.
So what is the Sandtronics? The Sandtronics is a product that aims to automatically sand heavy timber wood, which is wood that's 5 by 5 inches or larger. This product aims to fill the gap in the market where other products are either extremely expensive or not practical for a use case. This product is aimed towards saving time for small and medium-sized companies as well as woodworking enthusiasts.